Okay, perfect. Okay, so get the handout. And while you're at it, there's a link here there's a link to the OSU Chem Demo Labs Instagram page. They are setting up all of the cool demos that I'll do during the session today. So be sure to check them out. They post all the time. How often do you guys post? Once a week. So what I have linked here is a really cool and spooky demo that they did like a week or so ago. You'll see what I mean when I say it's a spooky demo, but I thought it was pretty cool. All right, so all right, let's get started. So what chapter do we want to start with? Chapter 3 or chapter 4? Okay, raise your hand if you want 3. Raise your hand if you want 4. Okay, not a lot of people want 4. I will point out, I'll point out that, so like my lecture to the Tuesday, Thursday lecture, we finished chapter 4 already. We finished all our lectures prior to our midterm for next week. So some classes might just be behind. So yeah, we'll start on chapter 3. All right. So chapter 3 is about chemical reactions and stoichiometry. Many of the learning objectives is, balancing chemical reactions, identifying them, and doing mole conversions using molar masses and whatnot. So let's just go through one of these low-hanging fruit questions, because I guarantee you there will be a balance this chemical reaction on the exam. But notice that our exams, we don't have you type things in like long equations. This is typically how we get around it. Here's an example where we could key this in on the exam. So consider the balanced chemical equation for the combustion of ethanol. So all the coefficients are the simplest whole ratio. What is the sum of all of the coefficients in the balanced chemical reaction? So this question requires you to balance it, but all you're going to do is report one number at the end. So that's how we're able to achieve that in a multiple choice, Carmen type exam. So let's approach this. We're talking about a combustion reaction. So that means we're taking this substance and we are reacting it with what? When you burn things, what does a fire need? Oxygen. So our other reactant here is oxygen. So we are going to react this substance with oxygen, and our two products are going to be CO2 and water. That is our kind of skeleton structure for our balanced chemical reaction. I'm going to do something sneaky here and just kind of condense this ethanol. Notice how there's the carbons and hydrogens are separate. So I'm just going to rewrite this. There's 2 hydrogens. How many total, there's 2 carbons. How many total hydrogens are there? 3 plus 2 plus 1 tacked on the end, so there's 6, right? Is that right? Can I count correctly? Okay, and then there's 1 oxygen there. So that is just the kind of condensed version of ethanol. That's useful for us. It'll be easier to balance. We need oxygen, then we make CO2 and water. So now the hard part is getting the coefficients. For combustion reactions, if you balance a combustion reaction in this order, you will always be right. Do carbons first, using CO2. Do hydrogens next, using water. Then you want to balance your oxygens last by taking inventory of everything on the reactants and product side. So let's do that. Carbons, hydrogens, oxygens last. If you do it in that order, you will always be right. So let's go about this. Carbons first. So 2 carbons, 2 CO2s. Agree? All right. Next, we do hydrogens. So there are 6 hydrogens on the reactant side. So how many should I put on the water should I put on the product side? 3. All right. So when you do it in this order, we leave oxygen for last because we're going to just kind of take inventory of all of our oxygens and fix the number so they're the same value on each side by just changing the coefficient in front of the oxygen gas. So what I do is add up all of the oxygens on the product side because we're done with that side. How many oxygens come from CO2? So in each CO2, there's 2 oxygens, but there's 2 carbon, or 2 molecules. So there's a total of 4. And then how many come from water? 3. So that means there are 7 oxygens on that side. So I need to achieve 7 oxygens on this side as well. All right? But here's the thing. Does the oxygen only come from O2? It does not. So some students might try to put 7 halves in here, but that's actually not what we want to do. We want to take an account the 1 oxygen that's coming from the ethanol. So that means how many oxygens should come from the oxygen molecule? 6. Yes, 6, because 1 plus 6 is 7. All right? So that means what should the coefficient in front of O2 be? 3. Perfect. All right? And that would be our answer. So all of our coefficients, there's an implied 1 in front of ethanol, 3 in front of oxygen, 2 in front of CO2, and 3 in front of water. We can't make you write this out on a Carmen quiz. So how we get around that is ask you to give us the sum of all of the coefficients, or maybe we'll say, what is the coefficient, the sum on the product side, or what is the sum on the reactant side. But do remember, if you don't have a coefficient there, then there is there's an implied 1, and do include that in the count. So what we would report here is whatever 1 plus 3 plus 2 plus 3 is. What is that? 9? 9. So you would just type in 9. That's how we get you to do it on a multiple choice exam. All right? Okay, so how do we feel about that? All right, good. Okay, so let's look at the second one where we're kind of inspecting the basics of chemical reactions. So which of the following represents a decomposition reaction of a molecular compound? So this question kind of is twofold. We want a decomposition reaction. So other than combustion, which is reacting with oxygen to make CO2 and gas, the other 2 reactions we studied are a decomposition reaction, which looks like this. You start with 1 thing and you end up with 2 or more things. That's a decomposition reaction. On the other hand, we can talk about like a combination reaction, A plus B, whatever gives us C. That would be a combination, right? So we are looking for a reaction that takes on this form. So hopefully we can just eliminate a bunch of these, right? So A, is that a decomposition reaction? It is one. B, is B a decomposition? Nope. What kind of reaction is B? Combustion, yeah. What about C? Is that a decomposition reaction? Yes, but what about D? That one's combination, so we can eliminate B and D. All right? So you might be sitting there, oh, this question has 2 answers, A and C. Both of them are decomposition reactions. But is that the only qualifier that question asks for? No, it's decomposition, and it has to be of a molecular compound. So we have to pull out of our back pocket some chapter 2 ideas here. So this first reaction is a decomposition. The second reaction is of a decomposition. But the first one, what kind of compound are we decomposing? Just try to name it. It's an ionic compound. So is A the correct answer? It is not. So C is the correct answer, because let's look at this reactant. Is that a molecular compound? Yes, sure it is. It's hydrogen, oxygen, all nonmetals. That is a molecular compound. All right? All right, so that's balancing reactions. So let's do some mole conversions practice, and then I'll maybe do some demos. Okay, so 2 really big numerical ideas that we work with in chapter 3 is Avogadro's number, molar masses, and we learn about stoichiometry. All of this revolves around the idea of a mole, where a mole is just a number. It's like me saying a dozen of something. Like if I say a dozen, what number comes into mind? 12, yeah. So if I have a dozen eggs, you think 12 eggs. If I have 2 dozen eggs, that's 24 eggs. So to chemists, we want to scale up the number of atoms or molecules we're working with, because very rarely in lab are you ever working with like one singular atom or one singular molecule. So we want to talk about a large amount of particles that we can actually weigh out on scales and balances in lab. Can you tell me, what is the unit on the scales and balances you use in lab? A gram amount. When we learned about the masses on the periodic table, what were those units? Like when we talked about like isotopic masses and stuff, what was the unit off of the periodic table for a single atom? AMU, yeah, AMU, what does that stand for? Atomic mass unit. Do we have anything in lab that can measure atomic mass unit? Nope, it's all grams. So that's the purpose of a mole, okay? Because if I'm talking about one carbon atom, that thing weighs 12.01 AMU. But will you ever hold one carbon atom? No, it's way too small. On the other hand, we can use that same number off of the periodic table, scale it up to, oh, let's work with 1 mole worth of carbon atoms. What's really nice here is that the number stays the same, but now the unit is a gram. So 1 mole of carbon atoms weighs 12.01 grams per mole. That's really nice for 2 reasons. We can keep all of the numbers off of the periodic table. We don't have to like buy a new one. We don't have to make a new one. All the numbers are the same. And now we can talk about substances in a gram amount, which is what we can use in lab. All right. So all of these things depend on the mole. Here, Avogadro's number allows us to go from mole, 1 mole equals 6.022 times 10 to the 26 particles. Do we have to memorize this number? Are you sure we have to memorize it? Have you looked at the supplemental information at the back of the packet? I'm going to give you a second to look at it. Look at the last page of this packet and tell me, do you have to memorize Avogadro's number? No, you don't, all right? No, you don't. But at this point, I hope that, you know, with enough practice, you'll just know it anyway, and how to use it, all right? Remember, molar mass. Unit, gram per mole. It is an equality that we will use to do conversions, and then we'll do stoichiometry. This is with chemical reactions, all right? Okay, so let's actually answer this question. How many gold atoms are present in a small gold flake that weighs a tiny bit of grams? So the idea here is you can weigh a sample amount in grams on like a lab scale. And we can relate that to the amount of matter we have by using its molar mass and our Avogadro's conversion. So if you look up gold, gold has a molar mass of, what is it? 197 grams per mole, right? So I like, if you remember from our last review session, anything with a fraction in it, I always like to rewrite it as an equality so I can clearly see what 2 units I can relate or what 2 units I can convert. So notice here, 197 grams per mole. If you rewrite that as an equality, what that means is 197 grams of gold equals 1 mole of gold. That's what these molar masses mean. These are the weights of 1 mole of any of these substances. So actually, let me demo this real quick. Sorry, people on Zoom, you don't get to see it. All right? Yeah, so let me demo this real quick. Actually, let's finish the problem first, and then I'll do the demo. Okay, so let's use this molar mass to our advantage to figure out how many particles of gold we have. Let's start with the piece of information given, and that's the mass of this gold flake. So 0.002582 grams of gold. I'm going to use the molar mass of gold. So where am I going to put the 197? So locate those units. That 197 number is going to go where? On the bottom, 197 grams of gold is 1 mole of gold. Great, now I have moles of gold. Am I done? No. If the question asks what's moles of gold, then yes, we'd be done, but we want individual particles. So this is where we're going to use Avogadro's number. It's like saying, oh, I know how many dozen gold particles I have. Now I just need to multiply by the definition of a dozen. But in this case, we are multiplying by the definition of Avogadro's number. So 1 mole of anything, in this case it's gold atoms, is 6.022 times 10 to the 23 atoms in this case. And so our answer, I wrote it down, is a big number. So 7.893 times 10 to the 18 gold atoms, all right? So here, look, this is a tiny, like you've used the scales and the balances in lab, right? You see how they go out to 4 decimal places. Trying to measure out 0.0025 like grams of something, that's a tiny, tiny amount. That's a speck of gold. That speck of gold still has 7 times 10 to the 18 atoms. So 7 with 18 zeros after it. So even a speck of gold that you can barely see still contains a lot of atoms. And that's the reason we use mole amounts. This is a huge number. Do you like to write scientific notation? No, it sucks. So let's scale it up to mole amounts so it's numbers that are useful for us, all right? So what we did here, we started with a gram amount of substance, we used its molar mass to get to moles, and then we used Avogadro's to go to individual atoms or individual particles, if that's what we were talking about. So you're gonna be using molar mass a lot. So let's talk about molar masses for a second, all right? So remember, molar masses, these are the same atomic masses we talked about in chapter 2, except we're just changing the unit, grams per mole. So whenever you see a number, a molar mass on that periodic table of an element, it is actually telling you how much 1 mole worth of that compound is. So let's look at copper real quick, all right? Copper, if you look at the periodic table, has a molar mass of 63.55 grams per mole. So if I tell you that this sample of copper is 1 mole worth of copper, tell me, how much does this sample weigh? 63.55 grams, all right? So this is 1 mole worth of copper. When we're in lab, we're not gonna be working with 1 mole, but if we weigh out the gram amount of sample that we have, we can use this molar mass conversion to determine what mole amount do we actually have. Okay, so let's do iron. If I tell you I have 1 mole worth of iron, what's the mass of this thing if I put it on a balance? It should weigh what? 55.85 grams, perfect. So it works with elements, it also works with compounds, okay? So here I have sucrose. This is just table sugar, all right? Table sugar has how many? 12 carbons, 22 hydrogens, 11 oxygens. If I would add up all of those molar masses of all those elements, it should add up to like 340 grams per mole. If I tell you this is a mole's worth of sugar, it's going to weigh how much? 340. And then let's do water, the last one. So water, 2 hydrogens, and oxygen, that has a total molar mass of about 18 grams per mole, right? So here is a mole sample of water. That's very, very small amount, right? Because it's 18 grams. So just think about what the volume of this is. The density of water is 1 gram is 1 milliliter. So if this is 18 grams, there's only about 18 milliliters in here, all right? You know how much about 18 milliliters is. It's not that much. It's like a little bit more than a tablespoon. That tablespoon of water contains 6.022 times 10 to the 23 particles, all jammed in there, all right? So that's kind of the power of molar masses. You know, we don't have to be working with mole amounts. We can always use these ratios, these conversions to help us convert to how many moles do we actually have. So I really encourage you to practice using molar masses given here, rewriting them as a conversion factor, all right? So notice 18 grams per mole, what does that mean? 18.02 grams of water equals 1 mole of water. So when we're working with dimensional analysis, changing units, we know to put the 18 in a place where grams will cancel, all right? So I really urge you to practice using that. So never do you have to memorize, do I have to divide or multiply by molar mass? It's all dimensional analysis that came from chapter 1. So if you drank my Kool-Aid back then, all of this unit conversions should be basically all the same. All right, so that's molar mass. So let's keep going. What else can we do with molar mass? All right, so let's look at a molecule. Here we have caffeine. It has a chemical formula of that, and it has a molar mass of that. So, like I said, with molar masses, just rewrite that unit so it makes more sense to us. The molar mass is 194 grams per mole, so that means 194.19 grams of caffeine equals 1 mole of caffeine, right? So if in A, I'm given, oh, you start with 0.729 moles of caffeine. Now that we've rewritten that molarity, or sorry, not molarity, molar mass like this, you can clearly see, where does the 194 have to go? On the top or the bottom? On the top, because what's the goal? We want to cancel that mole, so that means we put mole on the bottom, 194 grams up top, right? So this allows us to convert 2 grams of caffeine. So that has an answer. It's like 142 grams of caffeine is there, right? Okay, so let's work the other way. What if we start with an 84.6 gram sample of caffeine? Oh, how many molecules are there? All right, so what we're gonna do here is kind of like what we did in the previous question, but backwards. We wanna go from grams of caffeine to moles of caffeine, and then go one step further and go to molecules of caffeine, where we're gonna use, again, Avogadro's number, where 1 mole of anything is equal to 6.022 times 10 to the 23 of those things. So what I'm going to do is use molar mass of caffeine to convert this to moles. So where am I gonna put the 194, top or bottom? Bottom, very good, 194. Are you memorizing, oh, I need to divide by molar mass here? No, you're not memorizing anything. You're just canceling units. 1 mole. Because save your brain space for other things that are important, right? Not things like this, right? So we've converted the gram amount of caffeine to moles of caffeine. I don't need to stop and calculate it right now. I'm just gonna keep going on to the actual answer to get to molecules of caffeine. And so we're gonna use this conversion. So be very careful of how you write your units. Notice that I'm writing moles of caffeine. Mole can be very easily confused with molecule, all right? But they're not the same. So I actually write out the full word molecule. So 1 mole of anything here, in this case it's caffeine, is 6.022 times 10 to the 23 caffeine molecules, right? So individual particles. And that equals some number. You can look at my key, but I'll write it 2.62 times 10 to the 23 caffeine molecules or particles here, right? That's a lot, lots of caffeine. Okay, so let's do another one here. Now this time we're starting with a 25 gram sample of caffeine, but how many nitrogen atoms are there? So in this example, we're actually going to do the same exact steps as the previous one. We want to start with grams of sample, goes to moles of sample, go to molecules of sample, but recognize I'm not asking you how many molecules there are. I'm asking you how many individual nitrogen atoms there are. But if we can get to molecules, we can use the formula to help us get to individual molecules. So look at one of those molecules of caffeine. I give you the formula. If I have 1 caffeine molecule, how many nitrogen atoms do I have? 4, right? So if we calculate how many molecules we have, let's say we have like 10 molecules, then that means we have 40 nitrogens. So calculate how many molecules are there, just like in the previous question, and then at the very end, multiply your answer by 4. So I'll just do that work right now. So we're gonna do grams of caffeine. We're gonna use molar mass again. It's gonna look very familiar. So 194 on bottom, 1 mole of caffeine. Then I'm gonna convert this to individual molecules, right? 1 mole of anything, in this case it's caffeine, is 6.022 times 10 to the 23 caffeine particles or molecules, but we are not done. If we stopped, we would be in individual caffeine molecules. Now we're gonna use the full chemical equation, or sorry, formula, C8H10N2O2. Nope, it's N4, sorry, N4. And we're going to use that relationship for every 1 caffeine molecule. there are 4 nitrogen atoms. So this third question, really the only different step is this last one, all right, where we multiplied by 4 to get that nitrogen. If we wanted to calculate hydrogen, we'd multiply by 10 instead, all right? And then there's some answer, you can look at the key. I want to get to this last one because this one's the hard one. But I want to show you, it's actually, we already did this just backwards. So here I'm telling you, we have a sample that contains this many carbon atoms. How much does the sample weigh? So really what we're doing is the previous question, but backwards, all right? We are going to start with 8.54 times 10 to the 24 carbon atoms. Since I want to get to a gram amount, I'm going to convert this to a mole amount using Avogadro's number. So 6.022 times 10 to the 23 atoms, in this case carbon, is 1 mole. So this allowed me to convert this to mole of carbon, all right? Moles of carbon. Oh, why didn't you tell me that this was here? That's annoying. Okay, there we go. All right. So I used Avogadro's number to convert the atoms of carbon given to moles. This is the most common mistake students will do. They will do this. They'll go, oh, I'm in moles of carbon, so I'm going to do this. 1 mole of carbon weighs 12.01 grams. Okay? But when I do that, I'm calculating a mass, right? It's a mass, correct? But what am I calculating the mass of? Just the carbon, yes. Is that what the question asks for? No, I'm asking what is the mass of the full molecule? So there's a step missing here, all right? We're basically doing this, but backwards. I know how much carbon I have, so we're gonna use the chemical formula as a way to scale back to the molecule. Look at this chemical formula. For every 1 caffeine molecule, how many carbon atoms are there? 8. So where is the 8 gonna go in this next fraction? On the bottom. So let's write out that equality. Really what I'm trying to say is that 1 caffeine molecule equals 8 carbons. So I want to put the 8 moles of carbon on the bottom, 1 caffeine mole up top. 1 mole of caffeine up top. All right? Caffeine. All right, and so now we're not quite done. We will multiply by molar mass of caffeine, because the goal is to calculate what is the mass of caffeine, not of carbon. So 1 mole of caffeine weighs 194.19 grams. All right, so notice that these 2 questions, most students, they can get this one. The first one we did here, going from grams to individual atoms, most students understand how to get there. It's going backwards is really hard. Counterintuitive to think, okay, if I tell you how many atoms I have, scale back up to how many molecules there are so you can use the appropriate molar mass. This answer, 344 grams, all right, of caffeine. Another common mistake students will do is they'll forget this 1:8 ratio, and they'll just do Avogadro's number then molar mass. But remember that this molar mass converts moles of caffeine to grams of caffeine. If we just use Avogadro's number, we're at moles of carbon, not moles of caffeine, right? So that's using molar masses and Avogadro's number. You need to get very good at molar masses, because who's going to go on to Chem 1220? Like everyone, yeah. It's gonna be assumed you know how to do it, or it's gonna be assumed. So if you don't, and it's a struggle, practice 50 times until you get it right on the first time, all right? Because yeah, in 1220, it's gonna be assumed you know how to convert between grams and moles. All right, so an application of molar mass that can help us in the lab and help us determine what substances we're working with is using percent composition. So this percent composition data is looking at a chemical formula given, so like this last one, right? This is caffeine. I could weigh out to determine, okay, how much of my sample comes from carbon in grams, how much of my sample comes from hydrogen, how much from nitrogen, how much from oxygen, and I can get percentages. all right? I just use the molar masses off the periodic table and make sure to account for those subscripts there. There's 8 carbons, so the total mass of carbon is 12 grams times 8 of them, right? So we can use that data to calculate percent composition data and then go back to a chemical formula, right? So this is a learning objective to convert percent composition data, this is percent by mass, and turn it into an empirical formula, meaning the simplest ratio of atoms. So for example, this is caffeine molecule, that's its molecular formula. Is the empirical formula for caffeine different? Could you simplify that ratio? Yes. Yeah, so if we simplified this, if you look at those subscripts, you can see, oh, you can divide all of them by 2. So the empirical formula is C4H10, and no, I can't do simple math. What is it? 5, okay. Nitrogen, 2O, that's it. All right, so that is the empirical formula of caffeine. If I gave you the percent composition data of caffeine, all you could calculate is the empirical formula. All right, so that's what we're doing right now, but we're gonna do it for a different compound, all right? Some type of mineral that contains, what is this? Iron, aluminum, and oxygen. What is the empirical formula? So we're gonna use molar masses, but there's a problem. I give you all of these in percentages. So the strategy, if I give you percentages, is we need to turn those into gram amounts. The easiest way to do that is assume you have 100 grams of sample. Why 100 grams? Because then the math becomes easy. If I have 100 grams of sample, then how many grams of iron do I have? 32.1 grams of iron. And then how many grams of aluminum do I have? 31.1 grams of aluminum. And then I would have 36.8 grams of oxygen, right? So convert all those percentages into masses. And the reason we want masses is because now that I'm in grams, I can convert to moles of all those things, right? Because molar mass allows us to go from grams to moles. So we just have to use the appropriate weights. I give you the atomic weights here. This is the same number as molar mass. We just have to add the grams per mole to it, all right? So we can use these numbers to convert to mole amounts of all these elements. So that's our next step. Convert all of the gram amounts of the elements given to mole amounts. So iron is 55.8. So where is the 55.8 gonna go, on the top or the bottom? Bottom, okay. So 55.8 grams, 1 mole of iron. Before I take out my calculator, I'm just gonna write all of them because I need to get all of them anyway. So aluminum is 27 grams per mole, 1 mole of aluminum, and then oxygen is 16, so divided by 16 grams, 1 mole. So I write it all out and then only pick up my calculator once because I'm really lazy. All right, so there we go. Let's convert all of those gram amounts to moles. So we get 0.575 moles of iron is present in this sample. We have 1.152 moles of aluminum, and then 2.3 moles of oxygen. So what a lot of students will try to do is just start rounding these numbers, but we're not gonna do that, all right? We can't have fractions in the subscripts of a chemical formula. Do you ever see fractions in our the subscripts in chemical formulas? No, they're always whole numbers. They're always counting numbers. So how we turn these mole amounts into integers is by identifying what is your smallest number that you just calculated, right? So in this case, it's the iron, that's the smallest number. Then what we're gonna do is divide every single number we just calculated by that number. So we're gonna divide everything by 0.57, 0.57, right? Why do we do this? It's because then we guarantee one of these mole ratios is an integer, because any number divided by itself is always 1. So we force iron to have a mole ratio of 1, right? By dividing that smallest number by itself, right? So then when you divide these other numbers, you get some numbers here. So we get 1 mole of iron. We have 2.0034 moles of aluminum, and then we have 4 moles of oxygen. So we're getting a lot closer to an empirical formula. So now the question is, should I round? Should I round? Yes, I should round this 2 moles of aluminum to what? To yeah, because it's 2.0000004. Yes, this is basically 2. And so this will give us our empirical formula. This compound has an empirical formula of 1 iron, 2 aluminums, and 4 oxygens, right? So once you get to this step, the question is, well, when do I round, when do I not? When you round, we make it really obvious, okay? So let me give you some other numbers. What if we did this calculation and we got 1.998? Would we round? Yeah, probably round that 1.998 to 2. But what if we did this and we got for aluminum 2.5? 2.51. What if I did that? 2.51. Should I round up to 3? No, what are we gonna do? Multiply all of them by 2. The reason is 2.51 is basically 2.5. So if we multiply by 2, we get rid of that fraction. And what do I mean by multiply by 2? I mean multiply every single mole amount by 2. So it would be 2 irons, what's 2 times 2.5? 5 aluminums, and it would be 8 oxygens, all right? That's how that would work. We try to make it super obvious when you round and when you don't round. Let me give you another example, all right? Should we round 2.33? No. What should you do? Multiply by something. If you don't know, just guess and check. Just take 2.33 and start multiplying by random numbers until you get a number really close to an integer. What are you gonna multiply by? 3, because 2.33 is very close to 2 1/3. So you're gonna multiply everything by 3. What if it is 2.66? Are you gonna round? No, you're gonna do what? Multiply by? Also 3 again, because 2.66 is equivalent to 2 2/3, right? So notice that we're always multiplying by whatever that denominator is. That was probably something we all learned in math at one point, but I'm not good at teaching math. Okay, what are other examples? What if it was 2.25? Would you round? No, you would multiply by what? 4, because 2.25 is the same as 2 1/4, right? So we try to make the numbers obvious. You'll never see something like 2.12121 or something. You're not gonna see that, all right? Because there it's not really clear what you should multiply by or if you should round. Honestly, if you do all this mole ratio and you get a weird number that you don't know whether to round or not, you probably did it wrong, all right? We try to make it very obvious whether you round or not, all right? Okay, how do we feel about that? Good, all right. Okay, let's do another one. So notice, we calculated the empirical formula, the simplest ratio. Technically, we didn't calculate the molecular formula because in order to do that, we actually need the full molar mass of the compound. We can't just use percent composition data. So if I tell you that you do an experiment and you determine glucose has this empirical formula, all right, CH2O. That's your empirical formula, your simplest ratio. But you want to figure out what is the molecular formula of glucose, all right? You need to figure out, oh, what's that multiplier, all right? So we actually need another experiment. Percent composition data will give us the empirical formula, but in order to get the molecular formula, we need something else. We need the experiment mass spectrometry. That allows us to determine what is the full molar mass or weight of the molecule itself. And that will help us figure out what is the multiplier between the empirical to the molecular formula. Let me give you an example of, I guess, something a little bit easier. What if I gave you a molecule, C6H6? Can you tell me what is the empirical formula? CH, yeah, we were really fast at that. So what was the multiplier? 6. So if the multiplier is 6, compare the weights of these two things. If you calculated the molar mass of each of them, which one's gonna be heavier? the full molecule, and it's going to be heavier by how much? By times 6. So that's what we're doing in this problem, except we're doing it backwards. I tell you the weight of the full molecule, right? This full molecule weighs about 180 AMU. So this is going to help us figure out, oh, what is that multiplier going to be, right? So we need to figure out how much does the empirical formula weigh. We can just be really kind of back of the envelope rough with this because we're just trying to figure out the multiplier. So I'm not going to use like exact molar masses here. I know carbon is 12 AMU. Hydrogen is about what? 1. So I'm going to add 2 because there's 2 hydrogens. And oxygen weighs how much? 16. So can I do that in my head? Is it 40? Is it 40? All right, so one empirical formula unit weighs 40 AMU. Do you see how I got that? I just calculated what is the molar mass of that? It's 40. Is it 40? It's 30, perfect. All right. Thank you. It's 30. All right, so one empirical formula unit weighs 30. The full molecule weighs 80. So what must the multiplier be? 6, yes, it is 6, okay? It is 6. So that means, what is the molecular formula? C6H12O6, right? So see how we work backwards there, right? And we needed to be given what is the weight of the full molecule. So you compare the weight of the empirical unit, and you figure out, okay, how do you scale up to your full molecule, all right? So you just compare the weights. All right, okay, good? Good, all right. Okay, now everyone's favorite, stoichiometry. And then I'll do my other demo. Is this the last one? Oh, dang, there's a bunch here. Okay. Okay, so we have a chemical reaction. All right, so we are using stoichiometry now. So we talked about Avogadro's number, we talked about using molar masses, now we're gonna use stoichiometry. So what stoichiometry is when you're given a balanced chemical equation like this one, notice we have these coefficients that tell us the ratio of molecules that need to react in this reaction. So these coefficients, as long as we know the mole amount of one of them, reacting, we actually know the mole amount of all of them because of stoichiometry. What these coefficients mean is it relates all of these different substances either reacting or being produced in the unit of moles. So what this means, all these coefficients, what it means 2 moles of iron will react with 2 moles of H3PO4, will produce 2 moles of this iron phosphate thing, will produce 3 moles of hydrogen. So we have a bunch of equalities we can use. I like to call it, if you're in the unit of moles, it's like your ticket to ride the bus wherever you want to go. Because if you know the mole of one thing, then you can figure out, oh, how many moles of iron do I need because of that stoichiometry. If you start with a mole amount of phosphoric acid, oh, you can go to moles of hydrogen if you want. Doesn't matter, because if you get on a bus, do you have to get off at a certain stop? No. Do you have to get on at a certain stop? No. But as long as you're in the unit of moles of something, you can get on wherever or get off wherever you want, because all of these coefficients relate all of the substances by moles. So if I tell you how many moles of phosphoric acid is reacting, can I just go ahead and use stoichiometry? Look at the unit that I'm in. I'm in moles. So can I use the coefficients? Yes, I can, yeah. So in this case, I'm going from phosphoric acid to where? To, where am I gonna get off the bus? Hydrogen. So we're gonna use those 2 coefficients. We're gonna use the phosphoric acid, H2 coefficients. So we see, oh, based upon those coefficients, you need 2 moles of phosphoric acid to make how many moles of hydrogen? 3 moles of hydrogen. okay? This step right here, this is called stoichiometry. Riding the bus, the coefficients, to go wherever you want to go in that balanced chemical reaction. So if we were done right now, we would be in the unit of moles of hydrogen. Are we done? No, because this question wants what? Grams. So what do we need to do? Molar mass. Yeah, so we're in the unit of moles of hydrogen, so we're just going to use the molar mass of hydrogen. And I think I give it up here. It's right there. 1 mole of hydrogen weighs 2.016 grams. And so you just calculate that. It weighs, what is it? This is 0.989 grams of hydrogen, right? Okay, let's do another one. If iron reacts, how much phosphoric acid in grams is required? So here, where are we getting on the bus? We're getting on the bus at iron, that's given. But we want to go to phosphoric acid. So let's start with what's given, 94.51 grams of iron. But what's the ticket to get on the bus? Can we do stoichiometry right away? Nope, you gotta do what? Yes, convert to moles. So 55.85 goes on the bottom, 1 mole up top. Now you do stoichiometry. What is the ratio? 2 to 2, so or 1 to 1, but I'm still gonna write it. So 2 moles of iron react with 2 moles of H3PO4. I'm not gonna skip this step, even though it's 2 to 2 or 1 to 1, okay? Okay, if we were done, we'd be in moles of phosphoric acid, but we want grams of phosphoric acid, so we're gonna use the molar mass of phosphoric acid. So 1 mole of phosphoric acid weighs, it's given in the problem, it's like 98, so 97.99 grams. All right, and there's your answer. So you're gonna be doing this a lot. You're given a gram amount of one thing, and you wanna figure out the gram amount of something else. What are the steps we did to achieve that? We did molar mass of the thing that's given. We did stoichiometry to go to the place we wanted, and then we did molar mass of the substance we actually wanted to get, right? You're gonna get real good at this. Molar mass, stoichiometry, molar mass. And it's the same deal in chapter 4. Instead of molar mass, we just use molarity instead. Molarity, stoichiometry, molarity. It's analogous. All right, so let's keep going. I don't feel like doing this one. Let's just skip it. You have the key, all right? It's just using Avogadro's number. You're fine, all right? Okay, let's do another one where it's actually limiting reactants. Do you really want me to do it? No, okay, all right. Do you want me to do this one? Yes, okay. Because here, I'm giving you amounts of 2 reactants. So here, we have a different reaction. I'm reacting 55 grams of magnesium, or sorry, 25 of magnesium and 55 grams of this other thing. How much aluminum solid is made, right? So here's the thing. In all of these questions, I just gave you one thing and you wanted to go to something else. But in this question, I give you 2 things. I want to figure out how much aluminum I make, right? I'm not smart enough to be able to just look at these numbers and know which reactant runs out first. So what I have to do is test both of them. I have to. I can't just look at them. A lot of students will be like, oh, it's the smaller amount. Nope, that's not always true. Oh, it's the one with the, the largest coefficient. Nope, that's not always true, all right? There's no trick to this. You literally have to do stoichiometry twice and check the numbers and compare them. You have to, right? Even I can't tell which one runs out first. So what we're gonna do is we're gonna pretend all of that magnesium reacts to make aluminum. And then we're gonna pretend all of that aluminum chloride reacts to make aluminum. And we're going to compare those 2 numbers. So we're gonna do stoichiometry twice. We're gonna do the molar mass, stoichiometry, molar mass strategy twice. So let's start with magnesium because that one's just given first. We'll use the molar mass of magnesium, so 24.31 grams is 1 mole of magnesium. Now that I'm in moles, I can use the coefficients. I can get on the bus to go to aluminum. Why do I want to go to aluminum? It's because the question is asking how much aluminum do you make. So I want to go to the aluminum product, not the other one. because it's not asking how much magnesium chloride I'm making, it's how much aluminum. So, okay, magnesium. So the coefficients there are 3 moles of Mg make 2 moles of Al. And I just want to go to grams because eventually that's what the question asks for. So 1 mole of aluminum weighs, what is that, like 26.98 grams, all right? I'm not even going to put that in my calculator yet because I want to set up the second stoichiometry setup. I don't know which one runs out first. So we're going to pretend, okay, well, let's pretend all of that aluminum chloride, the other reactant, all of that's going to react. How much aluminum do you make? So I use the molar mass of aluminum chloride because that's the substance I'm focusing on here. So 130 goes on the bottom. 1 mole of the stuff, AlCl3, goes up top. Now I'm in moles, so I can use stoichiometry. So the ratio here is 2 to 2. That's really nice, 2 moles, but I'm not going to skip this step. 2 moles of Al. Okay, because it's not always like, 2 to 2, a 1 ratio. I want to actually put what's there. And then go to grams, just like before. 1 mole of aluminum weighs about 27 grams. All right, perfect. So I did stoichiometry twice. So what I do now is calculate it. I get, if all of the magnesium reacts, 18.5 grams of aluminum is produced. If all of the aluminum chloride reacts, 11.1 grams of aluminum is produced. Which number matters to us? The smaller one, all right? This is my theoretical yield, the smaller number, all right? That's how much product I will actually make. So that means we located the theoretical yield. That means that this 55 gram aluminum chloride, this is my limiting reactant, all right? Okay, reactant. But then what does that mean about 18.5? Does this number mean anything to us? No, it means nothing to us because we will never, ever make 18.5 grams of aluminum product because the magnesium will never fully react. What this does mean is that magnesium, what kind of reactant is that? It's our excess. Yeah, so after this reaction is done, all of the aluminum chloride is exhausted, you will still have some magnesium left that is just lonely and won't react, right? So let's take a look at this. Like, I always hear students try to find like tricks to this, but look, this example breaks every single trick you've seen. The limiting reactant is the one that actually has the most mass. The limiting reactant is the one that actually has the smallest coefficient in front of it. So this one actually breaks every single trick that I've seen. I don't know, some students just try so hard not to learn it and just find the tricks. This is what you have to do. You have to do stoichiometry twice. I have a PhD and I can't look at these numbers and know which one runs out first. I actually have to calculate it, right? Okay, so aluminum chloride runs out first and we make 11 grams of stuff. So here is a follow-up question. It's the same numbers, but it's a lot harder, all right? Because here I'm not asking you how much aluminum you make. I'm asking how much of the excess reactant remains, right? So there's a couple ways you can do this. You can do a BCA table, but I'm not going to. I'm going to approach this a different way, all right? Don't worry, we'll do a BCA table in a minute, okay? So remember, with stoichiometry, once you're in moles, you can go anywhere, right? You can go anywhere. So in this problem, we always went to the product. We always got off the bus on the product side. But do you have to? You don't have to. So we already determined that magnesium is my limiting reactant. So this follow-up question, you still have to do this first step and figure out what is your limiting reactant for part B. But we're gonna finish the question in a different way, all right? Recognize magnesium is no, it's not. What's the limiting? Okay, it's the other one. Okay, that one's the limiting, sorry. So what we're gonna do here is instead of saying, oh, if all the aluminum reacts, how much product do I make? Instead, I'm gonna say, if all of the aluminum reacts, how much magnesium am I gonna consume? all right? So I'm gonna get on the bus, I'm gonna use the coefficients to instead go to the other reactant. That will tell me how much magnesium I'll actually use up in the course of this reaction, right? So it's actually a very similar stoichiometry setup. We're gonna say, oh, all 55 grams of that aluminum reacts. I'm gonna convert to moles so I can ride the bus, 1 mole. And then we will do stoichiometry. So 2 moles of AlCl3, and the goal is we wanna figure out how much magnesium we consume. So we're gonna put 3 moles of magnesium up top because that is what the stoichiometry says. And so we'll just multiply by its magnesium's molar mass. What is that? 24? 24.31, all right? This number that I calculate is going to tell me how much magnesium I consume, okay? So basically what we're saying, okay, if all of that aluminum reacts in this reaction, because it's the limiting reactant, how much magnesium will also react? So 15 grams. Is that my answer? No, my answer is actually what? 25 minus 15, so 10 grams of magnesium is gonna be left over. That's the answer, all right? So if you do all this work and you get a negative excess amount left, that means you picked the wrong limiting reactant, right? So this part B, this one is real hard. And honestly, I give you full permission to just skip this question on the exam because it's so time consuming. You've already taken one exam, right? Every question is worth the same amount of points, okay? So this question, if we gave you, okay, all of this, what's the excess reactant? This is 1 point. A is like, what's a strong electrolyte is 1 point, all right? So I give you full permission to skip this question and come back to it at the end, all right? If there's time, because I want you to answer all of the questions you can. And I don't want this question to eat up 25 minutes of your time so you are not left with enough to finish the rest of the exam, all right? Because this question requires 1, 2, 3 stoichiometry setups and the ability to interpret it, right? Okay, so, okay, let's do, let's do one more with percent yield, and then we'll do a BCA table. Yeah, then we'll do a BCA table. Okay, so here's a reaction, it's the same one. This reaction is conducted with 76% yield, and about 9 grams of aluminum is collected. How much magnesium reacted? So let's remember percent yield. Percent yield is actual over your theoretical. So everything we did in those previous couple questions, those were always theoretical yields. It always came from stoichiometry, from the BCA table. Your actual yield is what you actually like collect in lab, okay? Like what you measure on a balance or whatever, right? So when I say, oh, you do this reaction and you collect 8.95 grams of aluminum, is that 8.95 the actual or the theoretical? It's your actual, yes, this is my actual yield, okay? And I tell you, oh, this reaction has, it's only 76% good, like you only collect 76% of it. So how much magnesium did you have to start with in the reaction? So I hope you recognize, oh, we are given the amount of aluminum, we have to just back calculate how much magnesium we have. So it's just stoichiometry. But there's a twist here because it's percent yield, okay? So if with a 76% yield, I only get 9 grams of aluminum, how much aluminum did I aim for originally? Did I aim for less than 9 grams of aluminum, or did I aim for more than 9 grams of aluminum product? More, yes. So what we want to do, we're given the actual, we want to figure out what did this chemist, what amount did they aim for originally? All right, so we're going to calculate the theoretical. So we also know the percent yield as well. All right, that's given. So how I set this up is, okay, 76%, I'm going to put that as a fraction. So 0.76 equals the actual, so 8.95 grams over the theoretical. So what I'm going to do is I'm actually going to divide by that 0.76. So 8.95 over 0.76. This equals something, my key, equals 11.8 grams of aluminum. This is what I had to aim for. This was my theoretical yield. All right, this was, okay, when I did all that stoichiometry nonsense, molar mass, stoichiometry, molar mass, I aimed for 11.8 grams of aluminum, right? So I'm going to use this number to back calculate, oh, how much magnesium do I have to add to get this much aluminum? Because then with the 76%, I should land at that 9 grams that I actually collected. So that's the idea here, that we have to apply this percent yield. Since I gave you the actual, you kind of have to scale up and determine what was your original theoretical yield. So this isn't our answer. We're still a molar mass stoichiometry, molar mass step away. So 11.8 grams of aluminum. We'll use the molar mass. So what is this? 27, so 26.98 grams of aluminum, 1 mole of aluminum. Then we do stoichiometry. So 2 moles of aluminum is 3 moles of magnesium. Then I use the molar mass of magnesium, 1 mole, 24.31 grams, right? And then your answer, you had to have put 15.9 grams of magnesium in that reaction vessel at the beginning to achieve 11.8 grams of aluminum. But since you're only capable of collecting 76% of it, you're able to land at the about 9 grams that you actually collected. Okay. So here we go. Here's our BCA table example, and I think the next one also. And then I'll do a demo that's like a BCA table as well. All right. All right. So notice the past 3 reactions. Did I do a single BCA table? No. Do you always have to do a BCA table? No, you don't have to. But in these examples, these next examples are good instances for a BCA table. Here are the reasons. When we use a BCA table, BCA, what does it stand for? Before, change, and after. But the caveat of using these tables is that they must be in the unit of moles, or particles. But in all of these questions, were these in moles or particles? No, they were in grams. So not doing a BCA table for these questions is absolutely fine because it's too time consuming to convert all the gram amounts to mole amounts to put in a BCA table. But in this example, can you count how many chlorine molecules there are? Yes. Can you count how many fluorine molecules there are? Yes. Those number of particles can go straight into a BCA table. So in these examples, it's probably good to do a BCA table. Also, because a BCA table will give us a very comprehensive look at what's happening in this reaction, right? So here's the before picture. A lot of students, they ask me, they're like, how do I know what to put in the before line? You look at what's given in the picture. You look at the picture and you count how many chlorine molecules are there. Count. 3? 3. Do you agree? There's 3. That's where the 3 came from. I count 1, 2, 3 chlorine molecules. How many fluorine molecules are there? 3? 3. Okay. How many ClF3 molecules are there? 0. Very good. Okay. So we look at these numbers and we think which one of these reactants is going to run out first. I like to think of it this way, all right? Think of the coefficients. Look at each reactant separately. If I have 3 chlorine molecules and each reaction requires 1, how many times can I do the reaction with just chlorine? 3, because 3 divided by 1 is 3. Okay, do the same thing with fluorine. If I start with 3 fluorines and each reaction requires 3 fluorines, how many times can I do the reaction with fluorine? 1, because 3 divided by 3 is 1. So that means which thing runs out first? fluorine, the one, because we can only do the reaction once with fluorine. So with the limiting reactant, we are going to fully consume it. All right, a BCA table, usually when the numbers are easy, you can clearly tell what runs out first. So if I completely consume the limiting reactant, -3, I'm left with 0. But if I use up 3 fluorines, how many chlorines do I also use up? 1. This is where we use the coefficients. That change line has the same ratio as your coefficients. Do notice that I'm being very specific of the signs here. I'm consuming the reactant, so it's -1, -3. But then how much product do I gain? +2. Remember, I'm doing the reaction of once. Okay, so that means if I do the reaction once, I'm using up 3 fluorines, I'm using up 1 chlorine, but I'm actually going to gain two of those products. So then we add up all of our columns and we see that after this reaction's done, we're going to have 2 of those products and we're going to have 2 of the chlorines left. And we'll have 0 of the fluorines. And so we need to show which, or indicate which picture shows this. So notice that in this picture, we should have 2 chlorine molecules and 2 ClF3 molecules. These are what kind of compounds? Are they ionic or are they molecular? Molecular. So here's something kind of tricky here, because do you notice how some of these particles, they're like globbed together? They're like globbed together. Right? So we got to be careful because we want to make sure that our particle representation also matches what these compounds should look like. They're molecules, so we should see discrete particles. All right? So which picture is the correct one? D, because that's the picture that has 2 chlorine particles and 2 separate ClF3 particles. Remember, all of these are molecules, so that there should be discrete particles that you can like pick out, right? This question actually gave me PTSD because I'll tell you. So I went to graduate school here, right? So about 10 years ago, I was a bright-eyed, bushy-tailed graduate student, and they made all of us new teaching assistants take a Gen Chem exam. So like basically like the same final exam that you're gonna take eventually, they made us take it. But all of the questions were conceptual. They even told us, they're like, you don't need a calculator, right? When we went to this entrance exam. So I tried really hard on this exam. I don't know why. It didn't mean anything. It wasn't for a grade. It was literally for bragging rights, I think. And so I tried really hard on this exam, and I got one question wrong. Do you know which one I got wrong? It was this one, right? It was this one. Guess which picture I chose. Which one do you think I chose? A. I chose A. Why did I choose A? I knew this question was trying to get me to determine, oh, there are chlorine molecules left over. And I got that right, but what did I get wrong? I thought that the 2 ClF3s were like bonded together. They're not, they're separate molecules, all right? So yeah, this question gave me PTSD because I remember they like gave us our scores back and they went through all of the commonly missed questions amongst the whole class. And this was one of the tough ones. This is a common misconception. So yeah, this question makes me sad. So don't make that mistake. You won't make that mistake, right? No, all right. All right, let's do another BCA, and then I'll do a demo. So, here. Okay, so we have a mixture. So this is another example where a BCA table is really useful because why? All of the substances are given in moles. So can we put those numbers directly in a BCA table? Yes. Can we do that if I gave you gram amounts of stuff? No, you can't. So that's why we're going to use BCA tables. So here I say we have a mixture of only nitrogen and hydrogen in a closed container. The reaction starts to form ammonia, but then it stops. At that point, there is 5 moles of nitrogen, 3 moles of hydrogen, and 4 moles of ammonia. How many moles of nitrogen and hydrogen were originally present? So basically, we start this reaction with unknown amounts of nitrogen and hydrogen and 0 ammonia. That's what I'm trying to say. You start with, small amounts of those two things. Then the reaction happens, and then afterwards, what is in your container? You have 5 moles of nitrogen, 3 moles of hydrogen, and 4 moles of ammonia. So I'm trying to ask you, what did you start with? So we need to figure out our change line, because the idea here, usually we work BCA tables like top to bottom, but this time we're gonna work it bottom to top. So I'm telling you what's in our reaction vessel after the reaction. So this is what I like to call Sudoku your BCA table. Is there a missing piece that we can fill in this change line right away? Yep, right here, right? What is this number? +4, right? Because if we started with no ammonia and ended up with 4 ammonias, that means I had to have gained 4 ammonias. Great. What is the trick with the change line? Change line always has the same ratio as the coefficients. So if I made 4 ammonias, how many nitrogens did I have to consume? 6? Oh, let's write it out. Okay, 4 NH3s. What is the stoichiometry between NH3 to nitrogen? 2 to 1, so it's -2. You did the reaction twice. So 2 moles of NH3. So this is the stoichiometry step that I skipped, 2 moles of nitrogen, because I was hoping the numbers are easy. So we can do the same thing for hydrogen. Okay, if 4 moles of NH3 is produced, how much hydrogen is required? So you're just going to do stoichiometry, but this time go to hydrogen. So the ratio is what, 2 to 3? This time, so 2 moles of ammonia require 3 moles of hydrogen. So how many moles of hydrogen did you use? 6. Yeah, so it's -6 here. Right? And then work your way up. So what is the missing beginning piece of nitrogen? What is it? What is the number right here? 7. Yes, we started with 7 ammonias and 9 hydrogens. Right? 7 nitrogens, 9 hydrogens. The reaction partially moves forward and we make 4 ammonias, and we're left with a little bit of each of those reactants. All right? Okay, so there's another strength of our BCA table. So got some time left, so let's do some more demos. So here, let's do another kind of easy BCA table. All right? Okay. Here is a easy BCA table. Pretend this is moles. 4 moles of acid, 1 mole of base. The ratio, I'm going to just say, is 1 to 1. Can you tell me which thing runs out first? The acid or the base? If it's a 1 to 1. The base runs out. You don't know? Check, all right? If the base runs out, so just check. Just if the ratio is 1 to 1, we're going to consume all of our limiting reactant, so there's 0 base. So then how much acid do I also consume? What's the number that goes right here? 1 minus 1. So then we would have 3 moles of acid left. Okay? Then how much of the gas would you produce of this product? If it's all 1 to 1 to 1 ratio. Plus what? Plus 1. So then after this reaction, you should produce 1 mole of gas, right? If you pick the wrong one, you will get negative numbers. Pretend, oh, what if I think the acid's going to run out first. So -4, 0. But if 4 acids react, how much base should also react? 4. And then how much gas should you make? +4. But there's a problem. You get a negative number, so that is incorrect. Okay? So I hope with these numbers, you can clearly tell which thing is the limiting reactant. So tell me, for reaction A, which reactant runs out first? Base. So this is the limiting. So tell me, if the base is the limiting, how much gas should we produce in this reaction? +1. Okay, in reaction B, what limits us, acid or base? Base. So then how much gas will we make? +2. Okay, in reaction C, which one limits us? Neither of them. So this reaction actually fully reacts, right? Nothing limits us. So how much gas do we make? +4. What about the last one? Which one limits us? The acid. So even though, notice, we added more base, more base, more base, more base, but there's a certain point where we add so much base that it is no longer the limiting reactant, it's actually the excess one. So here, how much gas do we make in this example? +4, all right? All of these are mole amounts. So that's where a BCA table is really useful if it's all mole amounts. So I have these 4 reactions up here where I have the same amount of acid in all of these flasks, all right? The same amount of acid in all of the flasks, so like 4 moles. And I have different amounts of base in each of these balloons. So this reaction produces a gas. So by the size of the balloon, we should be able to tell how much product is made. So let's do them all. But in your head, think about what should the relative size of the balloons be for these reactions. So the first one's gonna look like this. Make a gas. Is it gonna be a big balloon or a small balloon? This is A, right here. Small. Then what about B? Big, bigger. Oh, geez. Oh no, my J. Crew. Okay, so then there's reaction C. This one makes 4 moles of gas. Are they getting bigger? Yes, okay, and then the last one, we're gonna add a butt ton of base. Oh geez. Okay, oh no, oh no, oh no. Okay. Okay. It's literally just baking soda and vinegar, but like, I don't want my blazer to get wet. All right, so there we go. We have 4 balloons, but let's compare their relative sizes. The smallest one's right here, where we only made 1 amount of the gas. Here, the second one, 2 equivalents of the gas. Then we had 4, but then the last one where we added so much base, it became the excess reactant. Notice that these 2 balloons are about the same size. All right, so there we go, because in this case, the acid is what limited us. All right, so there is an example of limiting reactants. I managed to stay dry. Great. Okay, so that is where a BCA table is useful. So we got 40 minutes. Let's do chapter 4. So 1, 2, 3, 4. Okay, we only have like 3-4 pages. Okay, so the first learning objective for reactions in aqueous solution. Hey folks, let's just remember, I'm not forcing you to be here, right? So, all right, so let's finish this up. So chapter 4, it's still reactions, but this time it's in solution. So there's special details we have to think about when dissolving stuff in solution. So here's one of the first learning objectives, is to identify whether a substance is a strong, weak, or non-electrolyte, right? So I have a demo where we will just go over the rules. There is some memorization that we have to do, okay? So electrolyte behavior has to do with how things dissolve in water. One of my favorite movies is Idiocracy, with one of the Olsen brothers. Yeah, Wilson, the Wilson brothers, Luke Wilson. He's the not as well-known one. But that's one of my favorite movies, and one of the quotes in it is, what's it? Brondo's got electrolytes, it's what plants crave. Electrolytes, it's dissolved minerals that are in Gatorades, in Powerades, and sports drinks, all right? So this is one of my favorite movies. It's about like they go into the future where humanity becomes really dumb and they water plants with Gatorade because they think plants want electrolytes, but they don't, right? So that electrolyte behavior in the movie is actually talking about dissolved ions, all right? So we can look at these particle views of how substances dissolve in water, and it actually has to do with conductivity. So we can do a conductivity test for electrolytes. This first picture has all ions present in the water. So what kind of electrolyte is this? Strong. So this is what you need to memorize, okay? Based on the composition of the compound, we can determine whether something is a strong electrolyte. Strong electrolytes include anything that is ionic, but it also has to be dissolved. I have to point that out. If it's a solid, then it's not a strong electrolyte. It actually has to be dissolved in water. Anything that's ionic. So if you try to name the thing and you use ionic naming rules, it is a strong electrolyte. So sodium chloride is ionic, so it's a strong electrolyte. Sodium hydroxide is an ionic compound, so it is a strong electrolyte. Potassium phosphate, ionic compound, a strong electrolyte. Or anything that is a strong acid. Yes, strong acid, okay? There are 7, you need to memorize them. I'm not gonna go over them, they're in your book. So you might be asking, well, what about strong bases? Strong bases are things like sodium hydroxide, potassium hydroxide. That's actually included in the anything that's ionic, all right? So yes, technically strong acid and strong bases are all strong electrolytes, but the strong bases is because they are already ionic, all right? Okay, so those are the things you look for strong electrolytes. If you have a solution and there's some ions, we call this a what? Weak electrolyte. My hand already wrote it before my mouth said it. So what you're gonna look for are weak acids or weak bases, okay? There's one weak base you need to memorize. What is it? NH3. Do you have to memorize the weak acids? No, because the strategy you use is if it's an acid and it's not one of the 7, it's a weak acid. There's only 7 strong acid. Every other acid on this planet is a weak acid, right? And then finally, things that produce no ions, all of these are molecular compounds, okay? So remember when we did like naming? In ionic naming, we did not have to say how many cations and anions there were because there were ions and we could predict the charges and predict the ratio. But with molecular compounds, how did we name them? We had to tell the reader exactly how many of each atom there was because there are literally no ions. So when you dissolve these things, you don't get any ions. So you get no conductivity. All right, so you're gonna look for molecular compounds. So here are the examples of compounds I'm gonna test here. All right, in the conductivity meter. So let's do this first one. So do you remember that these definitions, so I'll just zoom out a little bit. All right, those are my definitions. Pure liquid water, distilled water. What kind of compound is that? Molecular, right? Because remember, what are the rules for molecular compounds? All non-metals. But make sure, don't count acids, not acids, okay, because they're something else. Right? Water, H2O, all nonmetals, right? All nonmetals. So technically, water doesn't contain any ions, right? So, but what's the thing that we think of? You know, the saying, water and electricity, they don't mix, right? But here is pure water. And let's see its conductivity. I need to test this real quick and see if this thing is even on. Okay, yeah, it's on. Okay, so this is pure water. Based upon its formula, will it conduct electricity? Nope, it won't. There we go. Pure water does not conduct electricity. And so the reason is because we paid big money to remove any ions from it. That's why we call it distilled water. We distilled all of the impurities, any dissolved electrolytes that were in there. The reason we say, oh, electricity and water don't mix is because typically when we think of water, we think of tap water. Tap water has junk dissolved in it, right? It has minerals, you know, water hardness, that's just dissolved ions in there. So here is just tap water from the sink. Come on, go. No? How about this one? Is this one on? There we go. Oh, you see it? So you see a little bit of light there, and that's because there are some dissolved ions in tap water, but when we're talking about the expensive distilled water, no, there's no ions there. Okay, now let's do the next one, NaCl. What is that going to, what kind of electrolyte is that? Strong, yeah, it's gonna be a strong electrolyte. So when this dissolves in water, you get full sodium plus and chloride minus ions. So you're gonna see really, really strong conductivity there. Where is that? Salt. All right, here is salt. Wow, yeah, really bright. I like the enthusiasm. So then let's look at this one. That's salt. What about this compound? This is sugar, glucose. So do you think this guy will separate into ions? No. So you're just going to dissolve it. It's just going to be the same thing. C6H12O6, aqueous. So what kind of conductivity will this express? It's a non-electrolyte, so we won't see anything. So here is my sugar water. All right? So here's sugar water. Here is the salt water again. So here's sugar. Nothing. Nothing because there are no ions. This is a molecular compound, so sugar is not going to have any conductivity versus salt, and I'll just prove to you that, you know, it works. I'll use the same thingy here. There's salt. See? Tons of free ions able to conduct electricity. All right. Let's do these two. Sodium hydroxide. What kind of electrolyte? Strong. So when you, hey guys, let's get through this, all right? When you dissolve sodium hydroxide in water, what ions do you get? Sodium plus and what else? OH minus, very good. Where that hydroxide, that polyatomic stays together. Then let's compare that to, oh, I forgot. Sodium hydroxide is a strong electrolyte. It's a strong base. But what is the one weak base? NH3. And the reason this is a weak base is because, and it looks weird because there's no hydroxide attached to this compound that makes it obvious that it's a base. But when you put ammonia in water, what actually happens is that ammonia takes a hydrogen from water, leaving behind an OH minus. And this is why ammonia is a weak base, that only some of these ammonias will make hydroxide and ammonium, while some of them will stay together. So both sides of this equation exist at the same time. You make some ions, but not a lot. So when we compare the base, sodium hydroxide, boom, really strong electrolyte, and compare it to ammonia, this is a weak electrolyte, you see a lot dimmer light, and it's because it's a weak base. You only are making some amount of ions in solution, all right? And then the last one here, HCl and HF. Notice what kind of arrow I have here. HCl is another strong electrolyte. When you dissolve this in water, you get H plus and Cl minus, full ionization. But does HF fully ionize into its ions? No, you only get partial ionization to HF and F minus, where some of those HF particles are still intact and you get some ions, so this is a weak electrolyte. So if you look at this picture, that's what it looks like. This is like what HF would look like, some intact particles, but some free ions. So let's show an example of that. Whoops, sorry, where we have two acids. Where is my other acid? Okay, so here is HCl. HCl is what kind of acid, or what kind of electrolyte? Strong. Okay. Is that strong, you think? Yes. And then here's HF, a weak acid, so it's going to be a weak electrolyte, so very, very weak. Okay. It's actually not HF, it's acetic acid, but whatever. It's a weak electrolyte. All right, so there are our demos with conductivity. Okay. I just wanted one more follow-up. Oh, here's a couple more. So then tell me. Okay. If NaCl dissolves into solution, what ions do you get? Na plus and Cl minus. Perfect. If you dissolve magnesium chloride into water, what do you get? Mg2 plus and what else? Cl minus. But let's be super specific here. You get 2 of them. What if you dissolve sodium nitrate into water? What do you get? Na plus? Do you get separate N's and O's, or do you get just nitrate ions, like we talked about in chapter 2? You just get the nitrates, yeah. So the important thing here with polyatomics, in chapter 2, we put polyatomics together with cations, but in chapter 4, we're like separating them out again. But here's the thing, those polyatomics stay intact. So even though, we write NO3, when this substance dissolves in water, you actually just get that nitrate particle intact. So based upon these answers, which one of these solutions will conduct the most electricity? 1 molar of NaCl, 1 molar of MgCl2, or 1 molar of NaNO3? Which one will conduct the most electricity? B. Why B? There are 3 ions present in reaction B. While reactions A and C, there's only 2 ions, all right, 2 ions. But notice, if you got the nitrate thing wrong, then you would get the wrong answer there. And it's a very common misconception that folks think that nitrate splits apart. It definitely does not. All right, so, okay. Let's go through these really quickly then, because we got 30 minutes. Okay, let's just do a speed round. Tell me, strong, weak, or non? Potassium hydroxide, strong. Why? Strong base, or ionic. HNO3, strong because it's a strong acid. H2SO4, strong because it's a strong acid. H2SO3, weak. It is not one of the 7 strong, so it's a weak acid. SO3, non because it's molecular. NH3, weak. It's one of the weak bases we memorize. CaCl2, strong, perfect because it's ionic. CH3OH. Ooh, yeah, that one's tricky, yes. So what's tricky is if I asked you, okay, sodium hydroxide, what is that, strong, weak, or non? Strong, because it's ionic, it's a strong base. But remember, does OH mean that it's a strong base? Not always, because what is this? Is this a base? It is not. It's actually a alcohol. This is methanol. So this is actually a molecular compound. So it is a non-electrolyte. So just because there's an OH on there doesn't make it a base. It has to be attached to a metal. All right. So I tricked you. Okay. All right. So based upon this formula, what should a solution of ethanol look like on a particle level? A, B, C, or none of these? None of them, yeah, because ethanol is a what? Non-electrolyte. So should there be any ions? No, there should be no ions at all, okay? Do not make the mistake and think that, oh, this is like, analogous to sodium hydroxide. It is not. It is not the same as sodium hydroxide. Sodium hydroxide is ionic because it's a metal and an anion, a metal cation and an anion. Ethanol is completely no ions at all. All right. Okay, let's keep going. Okay, so let's do a net ionic equation, but in a neutralization reaction, which is just a special case double displacement reaction, where we're taking an acid and a base and making water. So we are reacting. This is acetic acid. So HC2H3O2, that's acetic acid. There's my acid. Yes. Strontium hydroxide, that is my base. Yes. Acids donate H pluses, bases donate hydroxide. Okay? So we're reacting these 2 things together. We want the net ionic equation for this, so we need to get the full balanced molecular equation first. All right? We need to balance it. So these 2 things are aqueous. All right? So let's think about this. when we build a double displacement reaction, what we want to do is do cation anion swapping. All right, so the cation on one compound is going to go with the anion in another compound. So what do we get? We're combining an H plus and a OH minus. What happens when you combine H plus and OH? What is that? That is H2O. Yeah, you might be, oh no, it's HOH. No, just rearrange the thing. It's H2O. Right, so one of our products is H2O. This is always a liquid for double displacement reactions. The other product is going to be what? Something with strontium and acetate. What are the charges of those? Remember, this is important. It's from chapter 2. Strontium has what charge in this compound? +2, and this one has -1. So my other product is going to be strontium with 2 acetates attached to it, 2 of them. Right? If you look at the solubility table, you'll see that strontium acetate is soluble. All acetate containing compounds are soluble. All right? Okay, so is this balanced? Not quite, not yet. We got to balance it. Because notice we have 2 hydroxides, but only 1 water. We have 2 acetates on the product side, but only 1 on the reactant side. So you can balance the acetates together. You don't have to balance the separate carbons, the separate hydrogens, the separate oxygens. Just look and see, oh, there are 2 acetates on the product side, so I need 2 acetates on the reactant side. So what should I put in front of this acetic acid? 2, right? So I have 2 acetates, but now I have 2 H pluses, but that's good because I have 2 hydroxides. So that means I will make 2 waters. Now this is balanced, right? So I react 2 equivalences of acid to react with 1 equivalence of the strontium hydroxide. Notice that there's 2 base units on there to give water and strontium acetate. This is the full molecular balanced equation. Now let's get our ionic equation, full ionic. So what we have to do is split things into its ions, but the only things that we split are things that are both strong electrolytes and they have to be aqueous, all right? You're looking for things that are strong electrolytes and they are aqueous. So if you have something that's a strong electrolyte and it's a solid, do you split it up for the full ionic equation? No. It has to be 2 things. It has to be a strong electrolyte and aqueous. So I like to go through every single thing and ask myself, is it those 2 things? If it is, then I split it. So this first thing, is it a strong electrolyte? It is not. Yeah, acetic acid is what kind of acid? Weak. So do we split this guy? No. So I'm going to put no split. Okay. The next one, strontium hydroxide. Is that a strong electrolyte? Yes. Is it aqueous? Yes. So we split him. The next one, water. Is it a strong electrolyte? It is not. Oh, it's a liquid. All right. So that automatically disqualifies it. So no split. All right. What about strontium acetate? It's aqueous. Is it a strong electrolyte? Yes, it's ionic. So yes, we're going to split it. So we're only going to split the things that are both strong electrolytes and aqueous. What you'll notice is some double displacement reactions have all ionic compounds, and what a lot of students do is they just split everything and they forget about the phase. So remember, it has to be aqueous also. So let's rewrite this where we split things that we're supposed to split. So I'm just going to rewrite the acetic acid again. Remember, it's a weak electrolyte. It only partially ionizes. We're only splitting up things that are strong electrolytes. But we are going to split up that strontium hydroxide. So we get a strontium, we get 2 hydroxides. So we split these. We don't split water, so I'm just going to rewrite it as is. All right, and then I'm going to split that strontium acetate, so SR2+, and then we get 2 acetates out, so 2C2H3O2, right? So there we go. That is my full ionic equation. Now, to get my net ionic equation, we need to locate our spectator ions. A spectator is an ion that does not change at all from the product side to the reactant side. It's literally the same thing written twice. So here we have acetate acetic acid, but look at the product side. It changed. It became acetate with a minus. So that means this is not a spectator ion. But look at strontium. We have strontium 2+ here. What is it on the product side? Also strontium 2+. Are they identical? Yeah, so it is a spectator. So we're going to remove that when we rewrite our net ionic equation. Is there anything else that is a spectator? No, there's not. Hydroxide gets changed. It turns into water. So we see that strontium is the only thing that is a spectator ion. So to get the net ionic equation, we're going to just rewrite this whole thing without the strontiums. And what this does is it just like really cleans up this reaction so there's not as much stuff written, all right? We take out the strontium because it's not involved in the reaction, it's not changing identity at all, so we can clearly see, oh, our acetic acid is reacting with 2 equivalences of base to make 2 waters and a free acetates, all right? So that is our net ionic equation, right? So here are 3 different reactions, the full molecular, the full ionic, and the net ionic equation where we remove the spectators. Okay, we got 18 minutes, so let's do this hard stuff. Let's do oxidation numbers. All right? Okay, for oxidation numbers, why do we care about oxidation numbers? It allows us to easily predict, is something being oxidized or reduced in a chemical reaction? The definitions of oxidation and reduction, I think, are hard to follow, all right? What's the definition? Oxidation is what? Loss of electrons, right? Is that what it is? Yeah. And then reduction is gaining of electrons. What's the mnemonic there? It's like Leo goes grr, or like oil rig. I don't like that. Here's the reason. If I gain an electron, if I gain an electron, what am I being? Am I being oxidized or reduced? Reduced, yes. If I gain an electron, if you use like Leo goes grr or whatever, that mnemonic. But then how does my charge change if I gain an electron? I get more negative. And so isn't that weird? Like I gain something, but I become more negative. I don't like that. So that's why I just track oxidation numbers. If you track an element and its oxidation number goes up, it's oxidized. If its oxidation number goes down, it's reduced. It's as simple as that. I understand numbers. I understand when they go up or down. So that's what I'm going to do to track those oxidation numbers to figure out what's oxidized and reduced. So let's practice oxidation numbers. The trick is if you think charge, you will be right 98% of the time. So if I look at the oxygen in O2 gas, what is the oxidation number? 0, yes, because O2 is charge neutral. But if we wanted the carbon in this compound, we need to consider the oxidation numbers of everything. So and they have to add up to the total charge of the compound. So what we're looking at here is sodium carbonate. Sodium typically has a +1 charge, so that's its oxidation number. Another rule is oxygen almost always in a compound has what oxidation number? Not 2, it's -2, -2, a -2 in a compound. So we're going to use that to our advantage to figure out, okay, what does carbon have to be? Okay, so we're going to set up an equation. We have 2 nitrogens where each of them is a +1. So 2 times +1 plus whatever carbon is plus 3 oxygens, which are -2, have to add up to 0. Why 0? Because the whole compound is negatively charged, or 0 charge. So that means, what does the oxidation of carbon have to be? What is it? 4? Yeah, it's +4, all right? So that's the oxidation number of carbon. It's charge, it's charge. Well, the tricks are hydrogen in a compound, usually +1. Oxygen in a compound, usually -2. The exceptions are H2 and O2. Those two have 0 oxidation numbers, all right? So let's put that to use. Let's look at the single displacement reaction. What's oxidized and what's reduced? So my strategy is get oxidation numbers of everything. Track those numbers. So iron solid, what's its oxidation number? 0, yay. Let's do the easy ones first. What else has a 0? Tin, okay? Think charge and you'll be right. So what is the charge of that tin in this tin sulfate compound? +2. How do we know it's +2? Sulfate is -2, yeah. So that means this tin has a +2 oxidation number. What about this iron on the product side? What's its oxidation number? Also +2, okay? So what I'm gonna do here is just ignore the sulfates because sulfate is just a spectator ion. It doesn't change, so therefore its oxidation numbers don't change, all right, if it's a spectator ion. So I'm just gonna ignore them. We can clearly see what's changing here are the oxidation numbers of iron and tin. So how does iron change? Its number goes up. So it is being oxidized. So it is also the reducing agent. It's the thing that does the reducing. So things that are oxidized, they lose electrons, right? So if you lose negative charge, you become more positive. I don't like that. I just like to look at the numbers and see, oh, it goes up, it's oxidized, okay? Versus tin, it goes from +2 to 0. So therefore it is reduced because its oxidation number goes down. It's being reduced technically because it's gaining electrons. If you gain electrons, you get more negative in charge. So it's being reduced. It is the oxidizing agent, okay? So let's answer these questions. In this reaction, what is reduced? The tin sulfate is reduced, and what is oxidized? Iron solid is oxidized. So therefore, blank is the reducing agent. Iron solid is the reducing agent, and the SN2+ in tin sulfate is the oxidizing agent, right? Just being hyper-specific there. Okay, so now let's actually answer the first question that I skipped. Does this reaction proceed as written? Meaning, what is this? This is a redox reaction. So we need to use the activity series to see if a reaction will actually even happen, right? So we're going to use the activity series. So notice you are given this on the exam. And so how we use this table is we recognize a pattern. When the solid metal is above the cation on the activity series, a reaction will occur. That is the rule. You're looking for the solid. If it is above the cation, a reaction will occur. So we locate, where is iron solid? It is right here. Notice I highlighted iron solid. I didn't just highlight iron. I highlighted the species exactly, iron solid. Then we locate tin, but notice this is a tin cation. Technically it's tin 2+. So we have to locate, where is tin 2+? Where is that? It's right here. So does a reaction happen? Yes, because the metal is above the cation. Okay, so we can react iron with any one of these cations below it, and a reaction will occur. But if I react it with any one of these cations, nothing will occur. Because if it's the other way, if it's the solid is there and the cation is here, nothing will happen because it doesn't fit that mantra, solid metal above the cation. So yes, a reaction occurs. All right, I only have 10 minutes. Is there a certain question you want me to do? Number 15? 18. I don't want to do 18. I'm going to do 20. Okay. So let's do 20 and then we'll be done. And maybe I'll have time for this demo. Oh, they didn't bring me my other thing. Dang it. So here we're doing a neutralization reaction of solid calcium hydroxide by HCl. How many milliliters of HCl are required to neutralize this many grams of calcium hydroxide? So a chemical reaction is happening, so we have to write the balanced chemical equation of what's happening. It's a neutralization. We have a base reacting with an acid. Can you give me like a maybe a rough idea of what does that base to acid ratio have to be in this balanced chemical reaction. For every 1 calcium hydroxide, how many acids do you have to add? 2. Why 2? Because there's 2 hydroxides, all right? So if this was a reaction between sodium hydroxide and HCl, it would be a 1-to-1 ratio. But because calcium hydroxide has 2 base units per every 1 formula, this is a 1-to-2 ratio. We're gonna make products, but I actually don't really care about these because what I do care about is this ratio. I care about this stoichiometry, the 1-to-2. So I'm not even gonna finish balancing it, right? So the idea here is I give you how much calcium hydroxide you start with in a gram amount. I also am nice and give you the molar mass of calcium hydroxide. So if I start with the gram amount of calcium hydroxide, can't I use the molar mass given, so 74, 1 mole, to be in moles of calcium hydroxide? Can I do that? Yep. So now that I'm in moles of calcium hydroxide, notice that at this point, this question is no different from chapter 3. I just did a gram to mole conversion. But why do I want this in moles? Because now what can I do? Ride the bus, yes. We can go from moles of calcium hydroxide to moles of HCl that I need to do this neutralization reaction. So what am I gonna do next? I'm gonna use the stoichiometry. Where is the 2 gonna go? Top, 1 mole of calcium hydroxide, 2 moles of HCl. So if we finished right now, we would get moles of HCl. If this was chapter 3, we would use the molar mass of HCl to get gram amount, but we don't want that. This is chapter 4. I want how many milliliters, instead of a gram amount of HCl, I want how many milliliters of this concentration of acid do you need? So here's the big tip for chapter 4, and I'm sorry that we didn't get to spend more time on this, is that molarity, big M, means absolutely nothing to me. So I want you to rewrite it as an equality so it's meaningful for you. So big M, do you know what 2 units that relates? No, it's literally just a capital M. So rewrite it. Molarity means moles per liter. So if I rewrite this, what this means is 0.1500 moles of HCl are present in 1 liter of this solution. That is a very useful equality that will be helpful to me right now. All right, so look at this equality that came from concentration. I have a mole amount of HCl and it relates to a liter amount. What unit am I in right now? Moles of HCl. So do you see what I'm gonna do next? So instead of using molar mass to convert to grams, I'm gonna use concentration to convert to volume instead. Where is the 0.15 gonna go? On the bottom. It's gonna go on the bottom because if we cancel everything here, we're right now in moles of HCl. So I wanna put the 0.15 moles of HCl on the bottom so those 2 numbers cancel, all right? Leaving us with the 1 liter up top. And that's it, right? So really, this should look exactly like chapter 3, where we did molar mass, stoichiometry. In chapter 3, we did molar mass, but what did we do here instead? Molarity, okay? What you need to do is, I tell my class, when you go to bed tonight, say it before you go to bed, molarity is moles per liter. Molarities is moles per liter. So say that a bunch of times so you get into your head that that big M means moles of solute over liters of solution. So let's finish this out. When you do the math, you get that, I think you get 0.08997 liters of this HCl solution is required. Probably better if we report that in milliliters. So this is 90 milliliters of that HCl solution is required. All right, so we'll stop there. So thank you everyone for joining me. Put pen to paper, do those practice exams. For this question, yes, you should convert to milliliters because I asked you milliliters.